Let's dive right into a massive piece of process control, flow measurement. Whether you're moving clean water or some highly abrasive gold mine slurry, how you actually measure that fluid moving through the pipe changes everything. We're going to break down the two main families of flow technology today, because honestly, choosing the wrong one can easily turn into a $1 million headache for your plants. So think about this. What happens when your control room data looks, totally plausible, but is actually completely wrong? It's a huge danger in process measurement. Say you pick the wrong technology. Maybe you use a restriction device for a heavy slurry or low connectivity fluid. Your transmitter might still send a perfectly convincing signal right back to the controller. The system thinks, hey, everything's fine, but you're flying totally blind. You're risking catastrophic process failures and just completely ruining your equipment. But before we put these technologies head-to-head, let's quickly frame the role of flow in the broader system. In any flow loop, the flow rate is your process variable, or PV. It's exactly what is physically happening in your pipe right at that moment. What makes flow so unique, though, is that it's often the fastest, most responsive control loop variable in an entire cascade system. Since liquids are basically incompressible, any change in valve position instantly changes your flow. So this measurement is really a critical preview for how the whole system is going to behave minutes or even hours down the line. It's essentially a sneak peek at what's coming in Chapter 6. Which brings us to the main event, the clash of methodologies. On one side, we have energy extractive meters. These are the traditional devices that literally steal energy from the fluid to create a readable pressure drop. And then on the complete opposite end of the spectrum, we have energy additive meters. These measure the fluid while barely even touching it. So it's this fundamental philosophical difference in engineering. Do you force the fluid to work for you, or do you just sort of passively observe it? Let's start with Camp 1, which covers the energy extractive meters. These are the older, deeply trusted, but inherently obstructive ways to measure flow. The easiest way to picture this is to think of a multi-lane highway with traffic just flying along at full speed. Suddenly, every single car has to squeeze through one toll booth gate. That physical restriction slows down the traffic, right? And it creates this massive high-pressure backlog right before the gate. Well, in process control, an orifice plate is exactly like that toll booth. You measure the traffic, or the flow, by calculating just how much that physical obstruction drops the pressure from the upstream side to the downstream side. Inside this energy extractive camp, you've got a few heavy hitters that you'll see pretty much everywhere. The classic orifice plate is basically just a smooth disc with a sharp-edged hole right in the middle. We also have flow nozzles and venturi tubes. Now, their physical shapes definitely differ to handle things like turbulence or suspended solids, but their method exactly the same. They all reduce the fluid's energy to get a measurement. You force the fluid through a restriction, its velocity goes up, its pressure drops. We read the high pressure right before the restriction, the low pressure right after it, and then the square root of that pressure drop. That gives us our flow rate. There is a reason these devices are the bedrock of the industry. They're rugged, they're relatively cheap for large pipes, and they're extremely well understood. But man, the trade-offs are strict. That obstruction causes unrecoverable pressure loss. That means your pumps are going to have to work harder forever. On top of that, any turbulence completely ruins the reading. So you need these massive, perfectly straight pipe runs upstream and downstream just to calm the fluid down before it even hits the restriction. All right, let's shift gears and look at Camp 2, energy additive flow meters. Here, we're moving totally away from physical obstructions. To contrast with our toll booth analogy, imagine a police officer standing on the shoulder of that same highway with a radar speed gun. The officer is clocking the traffic speed without ever stepping into the road, without building a gate, and without touching a single car. The traffic just flows by, completely unimpeded. That is the exact philosophy behind the energy additive flow meter. It introduces a totally separate form of energy, maybe a magnetic field or a sound wave, right into the pipe to observe the flow, leaving the fluid's actual physical energy completely intact. Let's sort out the devices in this additive column so we can clearly separate them from those pressure drop tools. The primary players here are magnetic flow meters, usually just called mag meters, and ultrasonic meters. And for ultrasonic, you've got transit time variants for your clean fluids and Doppler variants for your dirty, slurry-type flows. But what unites all of them is their method. They all measure volumetric flow rate without putting any physical obstruction inside the pipeline. Let's zero in on the absolute workhorse of this group, the mag meter. The physics here are honestly just brilliant. Utilizing Faraday's law, the meter applies a magnetic field directly across the pipe. So when a conductive fluid moves through it, its charged particles are deflected, and that generates a tiny readable electrical voltage. You are literally turning your pipeline into a miniature electrical generator just to tell you the fluid's velocity. It's pretty amazing. And because there's absolutely no obstruction in the pipe, there is zero pressure drop. This is what makes mag meters the ultimate go-to choice for those really difficult applications that would absolutely destroy an orifice plate. Think abrasive slurries or raw sewage. Plus, since you're just measuring this generated voltage, it totally ignores things like viscosity and turbulence, which means you don't need those massive straight pipe runs to get an accurate reading. Okay, let's see how all this applies in the field with a quick real-world application check. Here's your scenario. You are designing a control loop for a produced water pipeline coming straight off of a processing facility. The liquid is basically just salty water. And you know for a fact the pipeline is guaranteed to operate completely full at all times. So, based on what we've just covered, which camp are you drawing from? Are you picking an energy extractive orifice plate or an energy additive mag meter? Take a quick second to lock in your answer. If you guessed the mag meter, you hit the nail on the head. This is the absolute perfect candidate for a magnetic flow meter. Since produced water is highly conductive, it's going to generate a super strong, clear voltage as it passes through that magnetic field. And because the pipe stays completely full, which by the way is a very strict requirement for a mag meter to accurately calculate total volume, you get this highly accurate linear measurement without adding any pressure drop to your pumping system whatsoever. But we do need to issue a massive warning right here. What if this wasn't produced water? What if instead this pipeline was carrying a pure refinery product, say liquid propane, fuel gas, or just a pure hydrocarbon? If you install the mag meter on that line, it would fail completely. Why? Because pure hydrocarbons are entirely non-conductive. You have no free ions to generate that tiny voltage. Your meter would literally just sit there reading zero, no matter how fast that fluid was moving. So this is a classic example of where you absolutely must rely on an extractive device, simply because the physics of the additive mag meter just will not work. We have really only just scratched the surface today when it comes to the physics of flow measurement. There are still some incredibly strict operational rules you have to know. So in part 2 of this explainer, we're going to dive into rangeability, looking at a standard 4-to-1 ratio versus much wider ranges for those times when your plant just isn't running at full capacity. And more importantly, we are going to uncover the absolute non-negotiable installation rules for mag meters. Because if you ignore these specific rules, you aren't just going to get bad data. You are going to find yourself pulling a massively expensive piece of equipment right back out of the ground. So how exactly do we avoid that $1 million mistake? Join me in part 2 and we'll figure it out together.